Swayam Prabha. Digital India. Educated India.
So, hello everyone, today I will discuss the kinetics of protein adsorption, protein aggregation. So, this is the second lecture of the module 5, the kinetics of protein aggregation. So, we will quickly rewind the last lecture. So, we discuss what is the aggregation of the protein and what is its effect, particularly if it is functionally inactive, also if it is associated with conformational diseases like neurodegenerative diseases, Alzheimer, Parkinson. Then how we can experimentally characterize the protein aggregation based on the TST fluorescence assay, residual protein concentration, hydrodynamic size and morphology. Then also we discuss what are the different factors which affect the aggregation of the protein. So, in the bulk we discuss pH, temperature, ionic strength and some denaturating salts or ions. In the presence of surface we discuss the effect of shear as well as the adsorption. Then finally, we discuss what are the different intramolecular forces responsible for the aggregation of a protein, and we discussed long range forces, particularly the van der Waals forces, short range forces, hydrogen bonds, hydrophobic interaction, ionic interaction, dipolar interaction. Also we briefly discussed about the electric double layer. So, in today's lecture we will talk about how we can determine the rate of aggregation, how quick or how slow is that aggregation process. So, we will try to see how we can monitor the aggregation kinetics of a protein. So, we will see what are the different way to understand the aggregation, particularly in the bulk, also in the presence of surfaces. Then we will just see, if you know the aggregation process, what will be the rate equation, or you can say the kinetic equations, and also in the last section we will see if you have experimentally monitored the aggregation process, then from the experimental data how we can decipher the kinetic parameters. So, the first thing, consider there is a protein in the bulk and it comes into the contact of surface during its application, storage and the transportation. So, in the presence of surface, the very first step is the adsorption. And also from the adsorption it will go to the formation of the aggregate. Also in the bulk it can form the oligomer, then it can go to the aggregate. So, a protein can aggregate only in the bulk, also it can aggregate only from the surface, but at the same time, so there can be simultaneous or parallel aggregation both from the bulk as well as in the presence of surface. So, let us consider this is a native protein. this is native protein. So, what are the different pathways how a protein, native protein can reach to the aggregate, and after aggregation usually precipitates are get separated because typically the aggregates are the insoluble. Now, from the native, the first one is it will go to the intermediates or some unfolded structure. So, you can say this is like a intermediate, and from the intermediates to it will go to the unfolded. Now, from the intermediate again it can go to the aggregate, or from the unfolded it can go to the aggregate state. This is the one. Second is, if this process is quite fast, so you can directly observe that native protein is directly converted to the aggregate. So, you can say the protein self association, or you can say the protein protein interaction. So, it is happening in such a way that either this first process native to unfolded is either very fast or it is absent. So, it can directly go to the aggregate. Now, the third step is, this is degraded chemically, the native is chemically degraded, or you can say the native protein is chemically modified. So, D is the chemically modified, and once it is chemically modified, then it can go to the formation of the aggregates. So, what we are seeing here now, native can also chemically degraded, as well as the unfolded can also degraded chemically, and then it can go to the formation of the aggregates. So, these are the three, you can say, major route. The first one is native to unfolded to the aggregate, second one is native is directly going to the aggregate, and third one is native protein is chemically modified or degraded chemically, and the degraded intermediate is converted to aggregates. So, these are the three, you can say, major pathways for the aggregation of the protein, and once there is a formation of aggregates, it is rich in the beta sheet, which makes it insoluble in the aqueous. So, usually it gets precipitated or deposited inside the cells or tissue, and as we discussed the last lecture, it is then once it is deposited, it is associated with various neurodegenerative diseases like Alzheimer, Parkinson's and Prions. So, these are the 1, 2, 3, but mostly we consider native is going to the unfolded, then from the unfolded it is going to the aggregates. So, during the unfolding, what happens? The hydrophobic core molecules of a protein get exposed, and then the hydrophobic core of the one protein interacts with the hydrophobic core of the other protein. They form beta sheet rich structure, leading to the formation of oligomer, then to formation of the aggregates, or you can say polymerization of the unfolded protein to oligomer, and from oligomer to the polymer or the aggregate. So, now how the aggregation happens in the bulk? So, if you remember, for the unfolding we require some external energy. So, that external energy can be the thermal energy, it can be the chemical energy. So, different external factor, if you remember, it can be the pH, it can be the temperature, it can be the ionic strength, it can be some other, let us say, external factor like shear. Shear, particularly here we are talking about the agitation. So, because of these external factors, it is getting some external chemical or thermal energy, which is causing a protein to get unfolded, and once it is unfolded, so there is change in its conformation, particularly its helicity is lost and the hydrophobic residues which typically located in the core are exposed. Then it lead to the formation of the nuclei, and once this nuclei is formed, then it go to the formation of aggregates. Then these aggregates or fibrils are released in the bulk. So, now considering this process, we can simply write the native protein is converted to the unfolded state, and from the unfolded it is going to the aggregate. So, typically we consider this native to unfolded as a reversible reaction. So, K 1 and K minus 1, and then from the unfolded it is directly going to the aggregates. So, this can further be improved. We can say that native is going to denature is going to oligomer, and oligomer is going to aggregate. So, we are adding one more step, that is the oligomer, or you can say this oligomer also we are referring as the nuclei. Now, depending on this rate constant K 1, K minus 1 and K 2, one can comment how slow or how fast will be the rate of aggregation. So, in the first case, if K 2 is very high, K 2 is much higher as compared to the K minus 1. So, it means all the unfolded proteins are getting converted to the aggregates, and they are very much rerouted towards the native conformation. So, in that case, all the molecules in the D state will be converted to the A state or aggregate. Other case may be when the value of K 1 is higher than the K 2, it means K 2 is slow. So, native molecules or native protein will be present in the unfolded state, but as the K 2 is very slow. So, either the rate of aggregation will be absent or it will be very slow. So, depending on the value of the rate constant K 1, K minus 1 and K 2, the aggregation process, it may be slow, it may be faster, or even it may be absent. Now, we can further simplify. Let us consider the protein as a spherical molecules, and here what we are seeing, the two molecules are combining, they are forming the doublet, then triplets, then two doublets are forming, or 1 plus triplets are forming. In this way, what we are seeing is at each step N 1 and N 2 or 2 N molecules are reacting to form the agglomerate or the aggregate. So, we can simply say this looks like a second order kinetics. So, we can say dN upon dt is equal to k into n square. Now, we are writing minus because the number of molecules is decreasing when it is going to the formation of the agglomerate. So, if we can solve this, it will be like minus dN upon n square k dt. This will be, let us say, n naught initial to n t. So, this will be like simply 1 upon n naught minus 1 upon n t into k into t. It is going 1 upon nt to 1 upon n naught. So, it will be like n naught minus Nt is equal to Kt into Nt N naught. So, you can take it Nt as a common, Nt equal to 1 plus N naught K T is equal to N naught. So, here Nt is equal to N naught upon 1 plus N naught into Kt. So, if you typically consider a protein molecule as a particle, and with time if you know what was the initial number of molecules or initial number of particles, and at the time t how many particles are left, then we can calculate what is the value of the rate constant or what is the value of k. Similarly, we can also calculate what will be the t half, means N t we consider N naught upon 2. So, if you put N t is equal to N naught upon 2 here, it will be N naught upon 2 1 plus N naught K T N naught. Now, t will be the t half, cancel out. So, now it will be simply t half is equal to 1 upon N naught into k. So, t half is very simple, 1 upon k naught into t. So, this says what is the half time for the aggregation. It means at the time of t half, the N t will be N naught upon 2. So, here we have simplified and we are considering that let us say protein molecule like a particle, and at one step 2 particles are combining together to form the agglomerate, and we consider, let us consider as a second order kinetics, and we solve it. So, in this way also, if you are able to monitor the number of particles, decrease in the number of particles with time, then we can calculate what is the rate of aggregation. Now, once there is a formation of the aggregate, so typically in the bulk the diffusivity or the diffusion constant is going to change, and the diffusion rate of aggregation is directly proportional to the diffusivity or the diffusion constant. So, d is the diffusion constant and a is the radius of a sphere, the size and d is the diffusivity. D is the diffusivity and A is the size. Now, similarly, if you consider the particle size is different, it means if a let us say dimer is interacting with a monomer, or a dimer is interacting with a trimer, or monomer is interacting with the trimer. So, in actual case it looks like the nuclei, once it is formed, then monomer is interacting with the nuclei. So, in that case the D1 and D2 will be different, and similarly the A1 and A2 will also be different, because we are considering 2 different sizes. So, K will be the 4 pi D1 plus D2 under bracket A1 plus A2. Now, if you remember, if there is a change in the particle size or hydrodynamic size, so accordingly the diffusion coefficient will vary, and experimentally, as we discussed yesterday, using the dynamic like scattering, one method we discussed to measure the hydrodynamic size, we can measure the value of diffusion coefficient using Stokes Einstein equation. It says diffusivity is the kT, K is the Boltzmann constant, is the temperature, 6 by eta A. Here eta is the viscosity. So, now if you combine these two equation 1 and equation 2, so it says if you I put the value of d over here, the K rate of aggregation is 4 kBt upon 3 eta. So, what it says, when there is a formation of the aggregates, there is change in the solution viscosity. So, you can say the rate of aggregation is inversely proportional to the solution viscosity. So, if solution is more viscous, then it is going to retard the rate of aggregation. So, if you can measure experimentally the diffusivity, you may be able to calculate the rate of aggregation. Also, if you can measure the viscosity, you will be able to comment on the rate of aggregation. So, typically if you want to measure the viscosity, experimentally we can use either a rheometer or a viscometer and to measure the viscosity of a solution. And here I have shown a recent finding which says that the rate of aggregation K and this is the eta viscosity. So, it is following the decreasing trend or the inverse trend. So, when the viscosity value is higher, rate is lower, when the viscosity is lower, the rate is higher. So, it says the rate of aggregation is inversely proportional to the viscosity. So, this was experimentally observed during the aggregation of a protein. So, if you can either monitor the viscosity, then also one can comment on the rate of aggregation. So, other method is the viscosity. You can, as I told, experimentally we can use the rheometer or viscometer. Also, if you can monitor the size of, or you can say the molecular weight of aggregate. So, how to measure the molecular weight of aggregate? We can go for the gel chromatography or the size exclusion chromatography. So, it says that viscosity is a function of concentration factor and the molecular weight factor. Now, the concentration factor to the power alpha, molecular weight factor to the power beta, this alpha and beta both are constant. Alpha and beta are the constant. Now, the concentration factor is the product of concentration into density and the molecular weight factor is the ratio of the average aggregate molecular weight to the molecular weight of the native protein. So, in this method concentration is known, density is known, only we have to find the molecular or average molecular weight of the aggregate. Why we are calling average? Because during the aggregation we may have the aggregates of different molecular weight. It may have oligomer, it may have the aggregate, further it may have different fragments of the aggregate, means different molecular weight of the aggregates. So, if you can monitor the average molecular weight of the aggregate experimentally using let us say gel electrophoresis or the size exclusion chromatography, then we can estimate the value of the viscosity, and which can again be correlated with the rate of aggregation. So, this was the aggregation in the bulk. Now, let us consider in the surface. So, whenever a protein comes in the context of the surface, very first step is the adsorption of the protein. So, now during the adsorption again various interaction between surface protein takes place depending on the surface properties. It may be the surface chemistry, the surface charge, the surface, you can say the roughness or surface chemical composition. Of course, it also depends on the what is the surface property of the protein. Then there will be different kind of hydrophobic interaction, electrostatic interaction, hydrogen bonding, and that adsorption process depending on the surface protein interaction results in the conformational changes. So, if you remember when we discussed during the adsorption process is monitored in terms of adsorbed amount, also in terms of change in the secondary structure. So, typically during the adsorption process results in the making and breaking of intermolecular interaction or making and breaking of different bonds which lead to the conformational changes, especially for the globular protein there is a loss of alpha helicity. So, once there is a conformational changes, in that case the hydrophobic core group may be exposed and that will lead to the multilayer adsorption. So, this multilayer adsorption it may serve as a nuclei, or you can say this is like a oligomer and from here onwards once there is a presence of nuclei it will again interact with the monomer of the protein, it will lead to the formation of the aggregates on the surface, and once the size of aggregates will be more than a critical size it will detach from the surface, or you can say detach from the nuclei and it will go into the bulk. So, in this way in the presence of surface the adsorption followed by the aggregation takes place. Now, if we consider surface properties, so two major class of surfaces, one is the hydrophobic surface, other is the hydrophilic surface. So, in case of hydrophobic surface as expected there will be hydrophobic interaction between surface and protein. So, typically the thumb rule says it favors the adsorption of the protein, but at the same time it depends on the what is the hydrophobicity of the protein as well. And as compared to a hydrophobic surface there will be less adsorption on the of a protein on hydrophilic surface. But experimentally it has been observed that in both the cases aggregation takes place. So, what does it mean is whenever there is adsorption it leads to the conformational changes. Now, what will be the difference of the aggregation process in presence of different surfaces where there will be the less amount of protein or the little change in the secondary structure. In that case the aggregation process may be delayed, or you can say if you remember the formation of nuclei we call as a lag time. So, lag time can be extended, even it can be extended to very long time, we can say infinite. In that case there will be no aggregation, but whenever there is adsorption it means some extra protein surface interaction is taking place and that causes the conformational changes of a protein, and of course, depending on the surface property, that conformational changes and amount of protein vary, but ultimately whenever there is a conformational changes, it may lead to the multilayer adsorption or formation of nuclei, and aggregation process has been observed on both hydrophilic as well as the hydrophobic surfaces. Now, if you remember this, we discussed how the protein adsorption takes place. So, protein molecules are there in the bulk, they go to the interface, and from interface they go to the surface, and once they come on the surface, so the first they attach, then it go for the rearrangement or the reorientation. So, we call this as a side on orientation, and this orientation we call as a end on orientation. So, accordingly we write the rate equations for the protein adsorption. So, this is a protein, it is coming on the surface. So, it is forming the P1S1, that is we can say the orientation of the adsorbed protein, or you can say the attached protein, also we are saying the end on protein. Now, this end on protein will occupy some extra surface CS, and it will convert it to the side on protein. So, first step is the attachment, followed by the rearrangement or reorientation. Now, either this P1S1 or the P1S2, whichever reaches to the, or you can say at the equilibrium, whatever conformation either end on or side on is present on the surface, and if these conformations have the favorable structure or the favorable secondary structure which favors the formation of the oligomer, then from here onwards a process of aggregation will start. So, up to here this is like a protein surface interaction, and depending on this conformation of the adsorbed protein, it will bind to the n number of protein molecule to form the nuclei, and once this nuclei is formed, then it will go to the, this is nuclei, the fresh monomer unit will bind to it, and then it will go to the formation of the aggregates or fibrils, and after the certain length of the fibril it will detach to the bulk. So, this is the common step, this is the common step between the adsorption and the aggregation. So, during the adsorption there is a change in the secondary structure of either adsorbed protein, it may be in the side on or end on orientation, and depending on the conformation of adsorbed protein, it may lead to the formation of nuclei, and this P1S n molecules have joined to form the oligomer. Then this nuclei can again, monomer can combine to nuclei to form the aggregates, or you can say the polymer. So, in this way we can simply write the rate equations, and as we discussed for the protein adsorption process, in the similar manner we should be able to solve these rate equations to get the value of rate constants. Now, let us say apart from going for the solving the rate equations, experimentally we have observed the rate of aggregation. So, if you remember, we can observe the rate of aggregation. So, this is time 1 in terms of the TST fluorescence. So, typically this is what is shown like this, Also we can observe in terms of residual protein. So, during the formation of the nuclei or the lag phase, to here you can say there is a very little change in the bulk concentration of the protein or the residual protein, but during the growth phase or elongation phase there is a rapid depletion of the residual protein or the bulk concentration of the protein. That is why when we are discussing how to determine the concentration of the protein, so we discuss, we do not use the colorimetric method, because this particularly if you just see this region, there is no significant change in the protein concentration, particularly in the bulk. But when there is a aggregation process, when aggregation starts, there is a sharp or rapid decrease in the bulk concentration. A residual amount have almost depleted and reached to the value of 0. So, in that case here we can monitor the bulk concentration using various methods like a colorimetric, or you can say the staining or labeling method, or even we can use some instrumentation like SPR, QCM. So, once the residual protein concentration is known, so either you can say this rate of decrease, or you can say the rate of increase of the TST fluorescence, it indicates the rate of aggregation. Let us consider this is a typical TST fluorescence curve with time. So, up to here there is a formation of nuclei, and as we discussed, the TST molecules only binds to the aggregates, that to its long axis, that length is 1.5 nanometer. So, till the formation of nuclei there is no specific structure of the aggregate, or you can say there is no beta sheet structure is available. So, TST does not bind. So, at that case there is a no or very little TST fluorescence intensity, and once the formation of aggregates start, there is a sharp increase in the TST fluorescence, that we call the growth phase. So, during the growth phase, if you can analyze what is the growth phase, so we refer this elongation phase or growth phase as the rate of aggregation. So, this is the lag time, this is the elongation phase, and this is a stationary or the plateau phase. So, if you have this sigmoidal curve, so we can fit different equations to determine the rate of aggregation. So, the first thing we can fit a sigmoidal model which says I t is equal to I max plus I max upon I naught divided by 1 plus e to the power t naught minus t upon tau. So, it says it will directly fit to the whole sigmoidal equation. Whatever we got the sigmoidal curve, this equation will fit to the whole experimental data, and from here we can calculate 1 upon tau e to the power, you can say this is e to the power k t. So, 1 upon tau is the rate constant k, and also the lag time we calculate like a t naught minus 2 times tau. So, if you fit this Boltzmann equation or sigmoidal model to the experimental data, we can get the value of both rate of aggregation as well as the lag time. Now, also in some cases if you see there is a lag phase is almost absent, directly it starts with the elongation or the growth phase. So, either the lag phase is, this process is very fast or it is absent. So, here you may consider like this. So, only if you have the data, or you can take the data of only the elongation phase, so that we can simply fit with the first either kinetics, or you can say the an exponential expression I is equal to I max 1 minus e to the power minus k t, and this k is the rate. So, if you fit, we can get the value of rate of aggregation. So, other method is you are having a sigmoidal curve, and only during these two regions, if you can draw a slope like this, so it will be y is equal to mx plus c, and this slope will be the rate, or you can say if we can draw a slope, but the slope should be particularly in that growth phase only. So, if you draw a slope like this, so this, if you draw a tangent like this, so this its slope or m value will be the rate. So, if you look here, if you are drawing this a tangent line here, then slope of this tangent line will be the, you can say, the rate of aggregation. So, apart from the fitting the kinetic, solving the kinetic rate equations, indirectly you are measuring the viscosity or the diffusion coefficient. If you are having this TST fluorescence data, or you can say the residual protein data, we may be able to fit either the sigmoidal model or exponential expression or a linear slope to calculate the lag time as well as the rate of aggregations. So, I will summarize here. So, today we discussed how the protein aggregation, or what are the different pathways of the protein aggregation. So, first step is native protein is going to intermediate to the unfolded, then it is going to the aggregates, and as the aggregates are insoluble, they precipitate in the solution, or you can say they deposit. Second step is that unfolding step is absent, the native protein is directly going to the aggregate. And now the third step is the first native protein is chemically modified or degraded to some other intermediate, and that intermediate is going to the aggregate. So, these are the three pathways we discussed for the aggregation of a protein. Then we discuss how aggregation proceeds, or you can say how we can analyze the kinetics of aggregation, particularly in the bulk. So, we consider 3 step: native to unfolded, that is a reversible step, then from unfolded to aggregate, that is the irreversible step. Then further we simplified it, we considered protein molecule as a particle, and depending on the number of particle we can analyze the aggregation process, and we assumed at each step there are 2 particles are combining to form a oligomer. So, we consider a second order kinetics, and then we solve it to calculate the value of its rate constant. Also, we can calculate the value of T half time of the aggregation. Then we consider now aggregation in the presence of surface. So, in the surface, the first step is the adsorption. So, we compare how we discussed in the last class to study the aggregation kinetics of the protein adsorption. And similarly, from the protein adsorption we get either end on or side on oriented protein, and depending on its particular orientation there may be the formation of nuclei, and from after the formation of nuclei there will be the aggregation. So, in the protein adsorption rate equations we have added two more rate equations, one for the formation of nuclei and other for the formation of aggregates, and those rate equations can be solved analytically or using numerical methods to get the value of aggregation rate constants. And in the last we discussed if we are having some experimental data like ATST fluorescence intensity or the residual protein concentration, then we can fit either the sigmoidal model or the exponential expression or a linear slope to estimate the value of rate constant or the rate of aggregation. Thank you.